I've already made a video on the Heathkit IP-28 power supply, and it's been up for a week or so at the time I'm making this video, but I actually watched it a couple of times, and some friends of mine who were into the same hobby watched it and made a few comments, and the more I watched it, I decided it just wasn't the best video I could have made under the circumstances. I wasted too much time on some kind of trivial stuff and didn't show some other things very well. So I've kind of rethought the whole video. I've salvaged parts of the original video and scrapped other parts, and I'm going to reshoot parts here. So hopefully this will be a better result. We'll see. But once this is loaded up, I'm going to remove the original version. So I'm going to talk about the history of this particular power supply, and I'm going to use Chuck Pinson's excellent book, Heathkit Test Equipment Products, available on Amazon. Here in the power supply chapter, I already have videos on the IP-18 and its clone, the IP-2728, which is just a restyled version of it. I've already done a video on the IP-27, which is a fairly high-end power supply in Heathkit's lineup, and that itself was just a restyled and reformatted version of the earlier IP-20. Obviously this has a taller case that wasn't so much in vogue, but it's pretty much the same circuit. There is one vacuum tube in here, used I think in the reference voltage supply, and in here they used a transistor to do that, or solid state parts, but otherwise same circuit. So I've done a fairly extensive video on the IP-27. In the works I have videos on the entire IP-2700 series of power supplies, and I need to do some restoration work on the example I have of that series. I have a 2718, which is coming in from a seller in Texas as soon as he gets unfrozen. And this video is going to focus on the IP-28. This was a contemporary power supply of the IP-27. In Heathkit's lineup, they didn't really have a ton of different power supplies. You had the IP-18 type, you had the IP-27 type, you had the 28, and then you had the 2700 series, and finally the 2718, and that was about it. That's in, of course, low voltage power supplies. They had other power supplies with higher voltage and AC, such as Variac type things, but in the lower voltage regulated DC supplies, this was it. So you can see right off that there's some similarities between the Big Brother IP-27 and the subject of this video, the IP-28. I think they may have come from the same design team. At least somebody was making them keep some commonality in the functionality and appearance. They both have a meter for voltage and current. They both have a switch under the meter for voltage and current selection of display. They both have the voltage and current indication lamps. They both have a selector for current and voltage range, and then a fine adjust within those ranges. Same thing here. The IP-27 had more ranges for voltage and current, and therefore used knobs to select them. Here you have 4 different ranges for current and a bunch of ranges for voltage, plus the lowest position is the power on-off switch on this model, and then the fine adjust knobs are on the bottom. On the IP-28, you only have 2 ranges for current and 2 ranges for voltage, so it's done with a rocker switch, and those are on the bottom, and then knobs for the fine adjust within those limited number of ranges. But otherwise very similar. The output terminals are just the same. The on standby selector switch is just the same. And since the IP-28 does not have a big selector switch to use as the power on switch, it uses a separate power switch. But otherwise, very similar. Even the philosophy of the voltage regulator has a lot in common with the IP-27. So I always consider these to be kind of sibling power supplies. They both were introduced in the mid to high 1960s. The IP-27 coming in a couple of years earlier in 1967, the 28 coming in 1969, and then both being discontinued after 1975. I probably mentioned in my video on the IP-27 that I bought one of those specifically because it's one of the first Heathkits I'd ever built as a project in high school. That the electronics lab I was in high school had a bunch of unbuilt Heathkits that needed to be built by the students, and this is one of the first ones, if not the first one that I did. I have no such nostalgic attachment to the IP-28, and I really just thought it was a unique supply in the entire Heathkit range. It is not a restyling of something else, and it's not the original version of something that came later. It's its own design, standalone, and that's really why I'm doing this video, just to explore it and demonstrate it. Just a little bit of what it says here about it. It's a straightforward, versatile, and easy-to-use power supply. Both voltage and current limiting are continuously variable in two switch-selected ranges. Voltage ranges 1 to 10 volts and 1 to 30 volts. Current ranges 10 milliamps to 100 milliamps and 10 milliamps to 1 amp. Maximum current is 1 amp continuous. Meter reads voltage or current. Lambs indicate which is selected. Provisions for external voltage sensing and AC or DC programming. Load regulation 50 millivolts from no load to full load without external sensing. 20 millivolts if you are using external sensing. Line regulation less than 25 millivolts change in output for 10% change in line voltage. Well, here it says meter accuracy is 3% of full scale. I'm not sure it's even quite that good, at least not with the one I have. Maybe it was originally. External programming AC or DC, replaced by the IP-2718 in 1976. Well, that's the this model here. It may have been replaced in the lineup by the 2718, but it is not just a restyling of this. It's about the same physical size, and even the case has a similar design, albeit a different color scheme, but the circuit is entirely different. So, and the 2718 is also a tri-power supply, a fixed 5 volt supply for logic circuits, and a pair of isolated 0 to 20 volt adjustable supplies. There is no adjustable current limiting on the 2718 either, although it does have current limiting just to keep it from being damaged on overcurrents, but it isn't an adjustable thing that the user can tweak. So it was replaced in the lineup with that, but it is not a direct replacement. Anyway, so that's the history of the IP-28. Now let's get into the meter itself. I didn't manage to keep any video of the way this power supply looked when I got it via eBay, but I did put together a screen capture here of the way it looked in the eBay listing. You can see it's in pretty rough, dirty, and mottled condition. So part of the restoration of this supply deals with just getting all the dirt off, repainting some parts, and doing some other cleanup. Alright, getting into the restoration of this power supply, I've already started on it. I cracked it open, I did some preliminary tests, and it's basically functional. The voltage control pot, which I've partially discombobulated here already, taken off the mounting hardware, it's really in bad shape. I doubt I can restore it properly even with some pot cleaner. So I'm going to try to replace that. I'm going to spray some deoxit into the switch contacts, but they basically seem to be working okay. The seller on eBay that sold this to me had done some remedial work on it already. Here's a 5K half-watt pot. It's one of the alpha ones. They sell the whole alpha lineup of potentiometers. And I've actually used these in production work designs. I've got this guy with the extra long shaft that I can cut down and modify. I also have to do some general cleanup of the front panel. It's not too boogered up, but it needs to be cleaned. I'm going to demount these guys if I can, because they're filthy. I'm going to probably find out these don't come off. They're probably stopped. Maybe. Oh, good. So I can throw those in a bath and clean them up with a toothbrush. I'm just going to go over the front panel with some alcohol. And then the meter is basically in good shape, and I know it works, but it's kind of cloudy. And once I try cleaning that up with alcohol and some label remover, if that doesn't do it, then I might try polishing this with toothpaste. That's always a fallback option. I also identified inside here one solder joint on this switch, which is a three-throw switch. And one of them is not soldered. There's two leads in it, and it looks like it's free of solder. Alright, I've deoxed all of the switches, of which there are 4. Well, the power switch probably didn't really need it, but the 2 switches that control the ranges and then the one that switches the meter circuit have been treated. And next thing to do is to look at this potentiometer. Well, this smaller pot I got has got a metric shaft of 6 millimeters diameter, which is smaller than 1/4 of an inch. It's 0.23 and some change inches. But this long shafted one, even though it's the same brand, comes to 1/4 of an inch. So this has the correct diameter shaft, which means I'm already going to not use this guy. I'm going to use this one. And I have to see about the shank, because I think these shanks are smaller too. Yeah, the washer from the old pot is 0.38 inches, which is 3/8 of an inch. So it's a 3/8 of an inch hole on the front of the panel. And guess what? It's got a smaller shank on it. I'm supposing these washers that come with it will be a fairly close fit, and they are. 5/16 of an inch. So I'm going to have to do something, make a little collar to go around the shaft and to space it out so it doesn't rattle around inside the larger hole. That shouldn't be too hard to do. I've got a lathe after all. Here's another conundrum. Heathkit never seemed to use anti-rotation strategies to prevent their knobs and things from coming unwound. They just used star washers on the bushings of switches, that's rotary switches and potentiometers, and this one's no exception. This pot didn't come with a suitable star washer, and I don't have any in my junk box. Probably not going to be too easy to obtain in that size. And anyway, it would just fall on the bushing I'm going to make, or the spacer, instead of on the panel, so it's not really going to help. What I really need to do is use the anti-rotation tab that's already on the pot. And I can easily drill a hole, but it's going to fall like right on the edge of the knob. And therefore it's going to be slightly visible, which makes me want to try mounting it like this, so that it at least will be on the bottom. Well, I've made the decision to rotate the new pot so that it's going to have the anti-rotation hole at the bottom. And I cut the old pot out. It's all on the wiring harness. There's a blue wire emanating from way down there, which I think I can strip just a little bit. This other one's also very short and hard to get at, but I think I can strip them adequately to tack on an extension wire that will then reach to where it needs to go. The white-orange wire I think is long enough where it can probably be made to reach, and the white-yellow wire, or maybe it's just white, can also probably be made to reach. Let me see which way that's actually going to end up going in there. If I mount this with the anti-rotation tab at the bottom, then these terminals will be on the right side. And that's actually good because at least two of the wires and this one blue wire will reach nicely over on the right side, so that's good. All I have to do is extend this one wire. Unfortunately, it comes from this switch down there, which has another blue wire coming off of it. It's kind of a daisy chain arrangement, but I can probably desolder that one easily enough and tack on a new wire that will then run up rather than try to extend this guy. So I think that's what I'm going to do. So I'm going to start on the meter face. I suspect it's just scuffed up pretty badly, but a lot of times people put labels on these and it leaves label residue, and that ends up being a lot of this crud. So I'm going to start off with my Tech Spray label and adhesive remover and just see what that does. Then I'll try the alcohol, and if it's a little mottled, that's fine, but if the clear part is that boogered up, I'm going to try the polishing and hope for improved results anyway. So after about half an hour's worth of rubbing vigorously with my fingernail just on the other side of the tech wipe to give it a harder edge, and using the adhesive remover and then going over it with the rubbing alcohol or the isopropyl alcohol, it looks a lot better. And even though there's still some slightly cloudy spots on it, it looks way better. As usual, the black plastic part, even with all the adhesive residue removed, is just rough, and I'd have to polish that so hard that I don't think it's worth the effort. I think that this is cleaned up enough that I'm going to leave it alone. Now I have to work over the front panel and see how much of the general gunk I can get off, but based on past experience, a lot of that's just practically burned into the paint at this point. I'm not going to get it all off, but I can get some of it off. You may have noticed that the needle's not pointing at 0 anymore, and that's largely because of all the rubbing. There's a lot of static charge built on here, and you can see when I touch it that the needle moves. I'm disrupting the static there. I've moved the static charge around a little bit with my finger. This will dissipate over time, and the needle will return to normal. The bottom of the case isn't too bad, but it still has the old, well, it has one foot and then just the sticky part left of the other 3 feet. Well, actually one of those already came off too. I'm going to be replacing those with new bump-on feet. but I have to peel these off and then get this guy off and then clean up that adhesive residue. Alright, the outer case has been cleaned about as much as I'm going to get it. Front panel cleaned up pretty well, but it still has a lot of mottling. It's just deep discoloration from whatever, but a lot of the gunk did come off, so it looks much improved. I tried to clean the dirt out of the grooves in these switches, and it's much improved is all I can say. It looks a lot better. But then there's this thing, this ugly thing. This really looks awful. The sides aren't too bad. It's this wrinkle finish paint. The top looks just pretty nasty. I think I may give this the same treatment I've given the other power supplies and so on from this series that I've restored. Put it in the hot soapy bath, go over it with a brass bristle brush, clean it up as much as possible, and if it still looks ugly, then I'm going to shoot it with that khaki sand or whatever it was paint that I have, the camouflage paint. That's it's not this shade though, it's the other shade. It's kind of funny because all those other ones and this are part of the same series, but it kind of looks like Heath maybe changed their color scheme a little bit with some of these, because this one has a noticeably darker case. So presumably tomorrow, when I get busy doing modifications, these things are all going to get their bath. I have to make that bushing. So I got my post-it note with the dimensions on there. And that's a job for another day. Okay, the top of the chassis cover is soaking in warm soapy water. And the knobs and the banana jack outers, whatever those are called, are also soaking in the same thing in a smaller vessel. There was no comparable paint in the hardware store, so if after cleaning this up, if the paint looks too awful, I'm going to give it a shot of the Rust-Oleum camouflage paint, the khaki that I used on the other Heathkit ones. Okay, the knobs cleaned up really nice. The case top, a lot of dirt came off of it. It got to be a lighter color, but it's got a lot of bad patches on it. And even though it's a bit darker than this khaki paint I've used in the past, Rust-Oleum camouflage, I'm still going to paint it because it just looks too crappy. But first, how to make the necessary bushing for these guys. It's a 15/16 versus 3/8 diameter, so a 15/16 ID and a 3/8 inch OD, which is 6/16, so it's a 1/16 inch overall distance difference, which is only a 1/32 inch thickness. That's going to be really thin. I'm not really sure what the best way is to make that. I'm kind of thinking that just making a piece of wire of the correct gauge and wrapping it around might do the trick. So making it out of sheet metal might be the best way to do it. Alright, I happen to have a 1/32 inch thick piece of aluminum, and it's really good to keep like metals on this. Introducing copper type metals next to aluminum isn't the greatest idea, so I wasn't too thrilled with that. I also had bought a couple of these things, which I thought might have about the right dimensions to turn down in the lathe, but again, it's going to be so tiny by the time I'm done, it sounds like a disaster waiting to happen. So I'm going to try the sheet metal approach first. I've used my digital caliper to scribe a cut line along the edge of this piece of aluminum. I've got my sheet metal shears here. So there's the 1/16 inch wide in this dimension strip of aluminum that's 1/32 of an inch thick. I got the piece of metal in there slightly off, a little bit skewed, so it's a bit thicker at this side, but that's just immaterial. I'm only going to use a little bit at this end. To give me a mandrel, I've got a 5/16 inch diameter drill bit. I'm just going to wrap it around the shank. So there's that. Used my fine metal cutting saw to cut it. I left a little bit of a gap in it so it can close up. Just mash it down on the anvil here. And I have the ring. Just like that. Okay, comparing the outer diameter of the old pot to the diameter with the ring on it, and it looks like it's about a perfect fit. That should be success. I've used my spring-loaded center punch to punch the hole for the anti-rotation tab, and I'm going to drill a pilot hole and then drill it out with the appropriate 0.11 inch diameter drill bit. There we go. I used some painter's masking tape to keep the metal shavings from getting into the switches or falling through the hole. At least more than necessary. Some obviously went through, but okay, I did a test fit of the pot, and you can see the the ring I made there. It's just about perfect, and the anti-rotation pin went in pretty as you please. It's not going to turn anywhere. Here's another view of the ring doing its job. It's trying to tilt out of there a little bit, but it does go in flush, so that's fine. Okay, the back of the knob is about 1/16 of an inch from the panel. And it looks like it's about, needs to go in about a 32nd of an inch still to be flat, although it's very close. I'm just going to take a little bit off the end. But the knob is fitting really well with that shim. It's got just about the right grip on there. So, one more time. And I've got my second coat on there. It's looking much improved. I don't think I need a third coat on here. It's looking pretty good. I don't want to put too much on, it'll cover up the wrinkle finish that was on there from the previous coat. Alright, time to go solder that pot in position. Alright, I've spliced those two blue wires that used to go to one terminal of the voltage control pot to a new blue wire, which is a little longer, and I've managed to restrip the ends of these other two wires, and they're long enough to go to the pot. So now I just have to mount the pot. Alright, pot's all soldered up. Hopefully I can still maneuver it into position with all these wiring harnesses in the way. There we go. That pot sets the maximum current when you turn the current knob all the way up. This is in series with that. So it sets the maximum current setting for this. I don't have any setup instructions for this. I tried to find some, but I reached out and none of the people I normally get help from had any resources in this regard. I decided to calibrate the full-scale high current adjustment pot in there. It's a wire wound pot, and the procedure for that was to set that pot, once again it's that one on the bottom of the case, full counterclockwise, set the current to the 1 amp range, set the voltage to the 30 volt range, turn the standby switch on, set the voltage to full scale 30 volts, switch the meter from voltage to current reading mode, short out the output terminals, and then adjust. The current will be low and reading the meter, go and turn the pot clockwise until it reads full scale or 1 amp. So now everything within here adds up as far as what the full scale is. The current limiting should limit it to no more than the safe value, and all we're doing is setting exactly what that is. So I did that now and it's spot on. Alright, the only thing that remains to do is a bit more testing, mostly on the current limiting feature, and put the top of the case back on, and it should be done. Okay, I wasn't absolutely convinced that that current limiting function was working quite correctly. I suspected Q6, this transistor here, even though it seemed to be testing okay in circuit. I desoldered it. I had a couple of spares of that I bought, new old stock. I just went ahead and soldered it in there. Now I've tried my test again. I've got a resistor substitution box here. It has 1 watt resistors in it. I arbitrarily selected it to 470 ohms and decided to pick 15 volts as the voltage I'm going to be working with. That's going to give me a value somewhere in the area of 33 milliamps. So what I do here is I crank the current all the way up to max. I have the meter or the range set to 0.1 amp. That's more than enough. Meter on voltage, verify I've got 15 volts, power supply is on, and now I should be going to read amps, and I'm on the top scale and it's just a little bit above 3, so about the 30 milliamps I expected to get. So now I'm going to turn the pot down, and I'm looking for a roll off in voltage to start. There it goes. It's starting to drop. It's nice and gradual. I bring it back up just to where it stops. So now I've got my current limit set to about 33 milliamps. Well, now I can go over here and turn my resistance box down to 330 ohms, which will draw more current. And I'll put the meter back in voltage mode. There I get a voltage drop. I'll go to 220 ohms. I get another voltage drop down to 150 ohms. Another one. Go back up to 470. I'm back to 15 volts. If I put the meter in current mode, I've got my 33 milliamps. I start decreasing the resistance, and it's holding the current there because that's the job. It's in constant current mode essentially. So that's working really well. That circuit is now working. It wasn't before. That transistor was bad. I'll turn my pot all the way back up. I'll switch it back to 1 amp. And call that a successful fix then. That was the only thing in question, and now I know it works perfectly. Let's do a detailed look through the inside. Okay, so here, looking at the back side of the front panel, you've got your meter. It's a 1 milliamp meter, and then it's internally scaled to show you voltage or current on the front of it. These are the back sides of the two indicating lamps. This is the back side of the current adjust potentiometer. Notice those 3 ball bearings. This is a planetary transmission there. It's a little bit hard to see, but if we look closer, you can see right in the middle of it is that small shaft that's right in the middle of the ball bearings. That's what actually comes from the front panel. And when you turn that, it rotates the ball bearings, and then the ball bearings roll against this ring here, this outer ring, and the ball bearings sit inside of a little frame that rotates with them. So I'm turning the front knob quite a lot here, and you can see that it's resulting in a very slow rotation of the ball bearings. And what it works out to is 10 turns of the knob results in 1 turn of the potentiometer itself. So it's gearing down the knob by an order of 1 to 10, or 10 to 1. 10 knob turns equals 1 turn of the internal potentiometer. Then here's the back of the voltage control pot. I'm talking more about that elsewhere in this video. This is the power switch. Let me zoom back out. The power switch, and then below it is the standby on switch. This guy here. And there are the output terminals, and the one without a wire up here. That's just the chassis ground. Looking down there on the bottom, that's the switch for voltage range, and that kind of bluish colored resistor. What is that, teal? I don't know what that is. That's a precision resistor that's part of that switch circuit. This potentiometer mounted to the bottom is a calibration resistor for the current limit potentiometer circuit. And then down below there's another switch, and that's the selector switch for the current range. It also has a precision resistor soldered directly to it. And let's see, it's a little hard to see again. There's another precision resistor down there. It's brown in color. And since there's circuitry so close to the bottom of the enclosure, there's some fish paper glued to the bottom to act as an insulator. There's some more circuitry there just on terminals mounted to the back of the meter, some more resistors, things that just make more sense to be mounted up in that part. And here's the back of the meter selector switch. It has the meter's shunt resistor soldered directly to it. Okay, now let's go around and look at the insides from the front. There's the power transformer. This terminal up here handles the primary side wiring, where the 120 volts or 240 volts incoming AC is connected, and there are jumpers here and here. By removing those jumpers, well, I should say first that with the jumpers here and here, that makes this transformer primary set up for 120 volt power. But if you were using this in a country that has 220 volts, 240 volts, somewhere up in that range, you would cut these two jumpers or remove them entirely and put in another jumper. I forget from where to where. It's probably from here to here, but a different arrangement of jumpers that sets up the primary winding of the transformer for that higher voltage. Down there is the main power fuse, and where the line cord comes in with its strain relief. Here is the one and only circuit board inside the power supply. There have been, well, there has been some remedial work done on this circuit board. This transistor here, Q6, was faulty, although it took me long into my testing to realize that it was faulty. Initially I did a test in circuit, which isn't always ideal, but it saves you from unsoldering all the parts. And it initially seemed like it was reading good with an in-circuit test, but then the current limiting function didn't seem to be working quite the way I thought it should after further study of the schematic. So I ended up replacing it with another part of the same exact kind that the Heathkit manual said should be in there, and then it worked much better. The previous owner of this power supply had changed out these two transistors. This transistor down here I think is original, as is this one up here. So there's, not counting the transistor on the back, the power pass transistor, there's 1, 2, 3, 4, 5 internal transistors, and 3 of those have been changed. The previous owner had changed these two capacitors here, which are in the reference voltage power supply, and he'd used a very cheap kind of capacitor, which I had very little faith in, and he also put the capacitors in with too low of a voltage rating. It was likely to be stressful on the capacitors, so I've replaced them with a nice quality Nichicon parts and at an even higher voltage than they were originally specified to have, just because that's what was readily available. And then these 3 blue capacitors, these axial lead ones, which were the original ones originally in those positions, they had not been touched by the previous owner. I replaced those also just for good measure, because this is quite an old device from the 70s, and you know, I didn't have much faith in those original capacitors lasting very long. So all the capacitors have been changed, but otherwise all the parts on here are original. I fixed a couple of bad solder joints in here. One of them especially was troublesome. That affected the shunt resistor on the meter was not soldered on one end, so it was making an intermittent connection, and whenever reading current on here it looked like the meter was faulty, but since it was working well in voltage mode I knew the meter wasn't bad. It had to be somewhere else, and it did turn out to be that unsoldered connection. Then here's the back side of the programming and sensing terminal strip. That is the entirety of the inside of this power supply. So here's a look at the controls of the IP-28. So we have a meter on the left, and this is scaled 0 to 10 on the top and 0 to 30 on the bottom. So that works for current or voltage depending on which range we're in. There are 4 variations of range, 2 for current limiting and 2 for the voltage. So in the voltage we can go from 0 to 10 Actually, it's not quite down to 0. You can never dial it completely to 0, but it's pretty close. We'll just say 0 to 10 volts. Or we have a higher voltage mode where it can go 0 to 30 volts. You pick that with this switch, this kind of stiff switch. And then when you're in the 10 or 30 volt range, then the voltage control pot takes you through that entire range. And the current can be generated in a range up to 0.1 amps or to 1 amp. And this affects the meter as well as the entire current limiting range. So if you're in the 0.1 amp, then 10 up here counts as 0.1 amp if you're reading current. If you're in 1 amp, then the 10 counts as 1 amp. Obviously it works as 10 for 10 volts if you're in the 10 volt range. Then there's a selector switch down here to determine whether the meter shows current or voltage. And the meter never shows directly, anyhow, the current limit set point, but it does show you the real-time current being pulled out and supplied from the power supply. There are these two lamps up here. If the meter is in current mode, then this lamp turns on. If the meter is in voltage mode, then this lamp turns on. So it's basically telling you which knob is going to have an effect on the meter. That's the purpose of these lights. It does not tell you whether you're in constant current mode or constant voltage mode. Many modern power supplies automatically switch between two indications like that. That is not the case here. It just tells you which knob will have an immediate and direct effect on what's being displayed on the meter, and it shows you whether the meter's in current or voltage mode in case you don't want to look at the switch down here. At the upper right is the power switch. Then there's the DC on standby switch, and all this does is it determines whether or not the red and black output terminals are connected to the internal power supply circuit or not. So if it's in standby, these are not connected to the internal power supply circuitry. If it's in DC on, then they are. So it's basically an on-off switch for the output. Everything else being the same. So that's the front of the power supply. Here's the back of the power supply. These two hooks are for wrapping up the power cord. This plastic object is the cover for the power pass transistor, which is mounted on the back panel to use as a heat sink. So that's what's under here. These are the sense and programming terminals. This power supply, as many good bench power supplies have, or has the ability to sense the voltage that's being regulated from the load itself rather than internally. So you think about what a regulated power supply is doing with its voltage. It's looking at the output voltage and constantly adjusting its internal resistance through the voltage regulator element, the pass transistor in this case. It constantly adjusts that to get the desired voltage and maintain the desired voltage at the load. In many cases, these output terminals on the front, if you just wire them through a few inches of fairly heavy wire to the load, the voltage at the load and the voltage at the output terminals is essentially the same. But you might be running the leads for a longer distance, or you might be supplying the full 1 amp output current and be using kind of maybe a bit smaller diameter leads to go to the load than you really should be, and you're getting a substantial voltage drop in those leads. So maybe you've dialed up 12 volts, but you're dropping a volt in the power leads, so the load's only seeing 11 volts instead of 12 volts. Well, with remote sensing, you can arrange it that the power supply actually looks at the voltage at the load rather than looking at the voltage at the output terminals of the power supply and using that voltage sensing to regulate the output voltage. These screws here, one marked plus and this screw here marked minus, these are electrically the same as the red and black terminals around on the front of the power supply. So you could just remove these jumpers here, these little metal jumpers, and the way it works is you unscrew two of them a little bit, you just loosen them up, and then these little jumpers swing away. They don't actually fall off, they stay in position, but they swing away, so they're not shorting these out and not shorting these out. And then you can run, and ideally should run, two wires from here and here out to your load to supply power to the load, and then run two more wires back from the load to the plus sense and the minus sense terminals. And that's what the power supply is then looking at to do the regulation. But many times we just don't care, and we don't want to run a duplicate set of leads out to the load for voltage sensing, so we just put these jumpers back into position, and it's essentially saying the power supply is only going to look as far as its output terminals, either these or the ones on the front, for voltage regulation purposes. Then these three terminals, and note one of them shares the plus sense terminal. If you want to control the output voltage of the power supply by an external means, instead of using the knob on the front panel as the only means of adjustment, you would remove this jumper. Again, you loosen the screws and swing the jumper away without actually removing the jumper. And once you've done that, you've essentially removed one side of the voltage control potentiometer on the front panel from the circuit. And if you then apply a DC voltage between this screw and this screw, minus here and plus here, as per the markings, what you're essentially doing is applying your external voltage across that front panel voltage control potentiometer. And if that potentiometer is turned full clockwise, then the full amount of your externally applied voltage reference is applied to the voltage regulation circuit. Let's say you applied a 20 volt power source or reference to these, and you turn the front panel knob all the way up. Now the power supply would be providing a 20 volt output, but it's not actually drawing any current from this. These are just a reference signal. It's basically copying the voltage it sees here, with a more powerful version being the output of the power supply. And then you could turn the front panel knob to, say, the 12 o'clock position, and that would take 50% of the reference, in that case 10 volts, and make the power supply's output 10 volts. And then if you raise or lower the voltage applied here, then the whole power supply raises and lowers with it. So that can be handy sometimes. It allows some programmability. For example, even today, you might have a little processor like an Arduino or something, and you could arrange to have a voltage output from one of its terminals and wire that up to here and have that Arduino control this entire power supply in terms of its voltage output. There's no way to remotely control the current limiting function. Now if you have an AC voltage, you can apply it, instead of across here and here, you can apply it between these terminals. And what that does is it actually puts the AC voltage in series with the internal reference supply and the voltage control potentiometer. It seems like a subtle difference, but it works better that way. And it's not intended to provide, say, an audio signal. It's not intended for very rapidly changing AC signals, but you could probably work with a a 60 hertz signal or something like that. relatively low frequency alternating signal. And what it actually does is it superimposes that AC signal frequency and waveform on the internal DC power supply. So in that case, you're adjusting the front panel voltage potentiometer to pick whatever the voltage is at the middle of your AC waveform, and then the AC waveform will modulate above and below that. If you had an AC sine wave, the middle of the sine wave would be whatever the voltage is you're picking with the front panel pot. And if you had that set to 10 volts, for example, then the middle of the sine wave would be at 10 volts and it would go above and below that voltage. So that's what these are for. But normally, for most operation, you just leave all three voltage or all three jumpers installed. So that's a review of the back panel. Okay, just a quick demonstration of the power supply in operation. I'm salvaging a bit of video showing the current limiting function from the original version, so I'm not going to redo that, but I am going to do just a quick look at the supply in its normal operation mode. So I've turned the current knob all the way up. It doesn't actually stop. That internal shaft on the planetary just slips once you get to the end of the pot's rotation. Then it turns easier in the other direction. If I turned it 10 turns counterclockwise, it would start getting stiff to turn again. So I've got it turned up here till it turns stiffly, so I know it's at full. I'm just going to put it on 1 amp mode so I can get the most out of the power supply. I'm putting the switch in voltage mode, and I'm going to go for the glory and set it up for 30 volts output range. Power is going to be on. I get the voltage light showing that the meter's in voltage mode. If I switch the switch, the other light turns on, back in voltage mode. I've got the output of the power supply connected to my programmable electronic DC load, and it's in constant current source, and I'm going to tell it I want to pull 500 milliamps, so 0.5 amps. So right here I can see that the load is set to pull 500 milliamps or half an amp. When I turn the power supply on, it will show me here the actual current being pulled and the actual voltage being measured. So I'm going to turn the load on. I'm going to turn the power supply on. I'm going to start with it fully counterclockwise here. Power supply on. I'm going to look at the meter, and I'm going to go up here and set it to what the meter says is 20 volts. This is only about a 5% accuracy meter according to Heathkit, so the load says it's actually only 18.5 volts. So I'm going to turn my voltage pot here until it actually gives me 20 volts. You can see that this is not that great of an accuracy. It should be down here, but there's no calibration for that. It's all coming down to tolerances on resistors, and it may be that these resistors don't have quite as close a tolerance as they did when they were new, but all the important resistors are wire wound type, so they really shouldn't change that much with age. So I don't know. It's just not that accurate of a meter when it comes down to it. So, however, the power supply is putting out 0.499, so essentially right on the money, half an amp of power. It is supplying the power requirements. I'm going to pretend like I don't care about accuracy and return it so it says 20 volts here. And looking here, it's still maintaining that. Now if I increase the current drawn by this load, I'll see that the voltage does not change. I'm just going to look at this here so I don't have to keep going back and forth between the power supplies meter. I'm just going to use the voltmeter here. So let's see here. So I'm over here, I've selected the most significant digit, and now I can change that with the knob. I'm going to 600 milliamps, and it shows that it is supplying that. 18.43 volts. Let me go back. 18.43. There's a slight voltage change, but it's very minimal as the current goes around. Now I'm down to 300 milliamps, 200 milliamps, and it's still 18 volts and small change, so it's holding the regulation pretty good. So that's proof that the voltage regulator is working. Well, let's try demonstrating this remote sensing feature. So even with the remote voltage sensing, I'm still only getting about 18.25 volts, thereabouts, 18 1/3, when the meter here says 20. So in this particular installation, the error is not due to voltage drop in these red and black test leads, because remote sensing isn't helping it at all. But in a situation where there's more current and or longer leads and you have a more substantial voltage drop, remote sensing like this can be useful. I've just shut it off after running it for about 10 minutes, pulling about 600 milliamps at 20 volts, and the back panel aluminum surrounding the power pass transistor is just slightly warm to the touch, so I can tell it's doing a bit of work. It's dissipating a bit of energy there. And honestly, I don't remember if I trimmed out the part where I showed this in the original video, so I'm going to show it again. I just have a little plastic bag with 1 or 2 spares of each type of transistor, which are the most difficult parts to replace if anything goes wrong on here. They're the most specific parts that really should be replaced with identical originals or something very close to it. So I've obtained those new old stock. They're all tucked into a bag here, and I just tucked it here next to the meter so that it will always be available with it in case I have to do a repair in the future. Okay, a final look around the outside with the cover put back on. And there's the bottom with the new bump-on feet. The positions of the feet and the corners here are dependent upon the cutouts in the sheet metal here. And then in the back, this one can't go there because of this screw, so I made this one symmetrical. I think that's more or less where the original feet were anyway. And I should mention that these are standard 3M bump-on feet, the kind that's still readily available. You can even buy them on Amazon. As long as they're black, as Henry Ford would say, they're readily available. The other colors are unobtainium unless you're willing to buy tens of thousands of them. Alright, I'm going to describe the theory of operation, go through the entire circuit on the schematic. A couple of words about this version of the schematic. This is my own redraw of the original Heathkit schematic because I was unable to find a nice, clean, legible copy of the schematic online, and I do not own a vintage copy of the manual. So, a bit of study, research, and close examination of my power supply, I was able to reconstruct the schematic and verify all details and all component values and wire colors and all sorts of things. And I found a few mistakes in the original Heathkit schematic and corrected those here. Starting over at the incoming side, we have our line cord defaulting to 105 to 125 volt AC range, 50 or 60 hertz, or anywhere in between, it doesn't matter. The ground pin is connected to chassis ground, and by extension to the green terminal of the output. The only other thing that's grounded to earth ground or chassis ground is the core of the power transformer. Everything else is floating. Here's the power switch. It's in series with the power fuse, and it is applied, or the incoming voltage is applied to one side of the power transformer primary. It's a dual winding, so that it can be wired with the two windings in parallel or in series. They get wired in parallel for the lower voltage range of the 110, 120 volt AC, and they get wired in series if you're doing the 220, 240 volt range. And these jumpers here are what gets moved around to arrange for that series or parallel connection of the primary windings. Regardless of which way the jumpers are done, this point here is always roughly 110, 120 volts. If the windings are in series, then half the voltage is across one and half the voltage is across the other. So the middle is roughly 110 or 120 volts if you've got a 220, 240 volt line voltage. So that's how they are able to come up with a constant voltage of around 110 volts to operate the neon bulbs on the front panel. Here is one gang of the meter switch with its current and voltage range, and it just energizes one or the other of these two neon bulbs with their current limiting resistors. So that's the front end of the power supply. Now, this voltage regulated power supply uses the approach of having a separately defined reference voltage source to control the main power supply circuit. And that's useful in situations where you have external programming. You can just control a voltage regulator off of a reference such as a Zener diode, but in that case it's more difficult to work in external programmability. So they do use the reference voltage approach. So there's a whole separate power supply down here. It has its own secondary winding. It starts out pretty high, roughly 72 volts AC. It's half-wave rectified with a diode and filtered with a capacitor. Then that's applied to a resistor Zener voltage regulating circuit, or at least a voltage dropping circuit. Produces 56 volts across the Zener. Then it's followed by another similar circuit, this time with a 36 volt Zener. So you end up with 36 volts here, and then over here is the voltage control potentiometer, and it's whatever voltage is produced by the wiper of this pot that controls the main voltage regulator circuit. So the goal is to impress a reference voltage across this potentiometer and then select from within that voltage with the wiper of the pot to control the bigger power supply. So in its normal arrangement, this side of the pot is always connected to the plus side of the reference voltage. The other side of the pot is normally through the jumper on the rear terminal, and that's the one that's shown across the AC terminals of that terminal block. It returns here and connects to the minus side of the reference supply. So if you ignore all this stuff over here, you could just say that this side of the potentiometer is connected to here. So it's really in parallel with this. Now this is a 5K potentiometer, and it's in series with a 10K resistor and a 510 ohm resistor. So the pot does not get the full 36 volts. It always gets something less because it's a three-stage voltage divider. You always have some voltage dropped here, some here, and some across this. And that's where the voltage range switch comes into play with its 10 volt or 30 volt selection. If the switch is where it's shown here, the 30 volt range, this dropping resistor is shorted out. So now the voltage divider consists of only the 510 ohm resistor and the 5K voltage control pot. Therefore you have a higher voltage across the pot, and therefore a wider voltage range to apply as a reference up here. But if you're in the 10 volt mode, now this switches over here. Now this resistor is not shorted out, and this resistor is the largest resistor in this divider. It's twice the resistance of this, so the majority voltage gets dropped here, and therefore you only end up with 10 volts dropped across here, therefore a smaller span of voltage controlling the bigger power supply. What about programmability? Well, if you remove the jumper here across the AC external programming terminals, now this side of the pot is no longer connected to this, although this side always remains connected. Now you could apply a slow changing AC signal across here. It ends up being connected in series between here and here. So you still have the reference voltage, but now you're superimposing the slow changing AC signal on that DC voltage. Therefore you get a varying AC signal here based upon the reference of this power supply here. Now if you're using DC programming, instead of applying an AC voltage from here to here, but with this jumper still disconnected, now you apply your DC voltage here, and it is applied directly across this voltage control potentiometer, and it's as if this doesn't even exist over here. It doesn't matter. Whatever voltage you apply externally here is on the pot, and then the pot selects from within that voltage and applies it up here. So that's your AC and DC external programming. Now for the main power supply circuit, I've broken it up into the supply voltage source, the constant current source, the pass transistor, and transistors because it has supporting transistors, the current limiting section, and the metering section. Let's start at the left. Here's the other secondary winding. It's a center tapped winding with the center tap connected to this line, which is connected all the way through to the black output terminal, or that's the minus output of the power supply. The two outer sides of the winding are connected through two diodes to this point. That makes it a full wave rectifier, and that's only possible for two diodes to be used as a full wave rectifier if they're coming off of a center tapped transformer winding. If this was not a center tapped winding, then this would be a half-wave rectifier, but as it is with the center tap and the two diodes, it is a full wave rectifier, and you're filtering it with a pi filter. It's called that because it has two caps and then the bridging resistor that its shape kind of resembles the Greek letter pi. These are two identical capacitors, and this configuration is more effective in ripple rejection than just one capacitor without the other resistor and capacitor. Anyway, so we're filtering here, and the first thing we do is we have from here to here this two transistor circuit, and the bottom of this circuit is actually not here, it's here. This is actually a voltage divider from here to down here. And what's this line? This is the minus sense pin, which is normally jumpered to the negative of the power supply. So you can think about this point here on this transistor being connected to here under most circumstances. This pair of transistors here in this arrangement acts as a constant current source. So it's always got the same amount of current flowing from here to here, and this transistor going down to here effectively acts as a variable resistor. So this is essentially the top resistor, and this is the bottom resistor in a voltage divider. With this being a constant current, the change in resistance of this transistor results in a proportional voltage being developed at this point in the circuit. This transistor is controlled by the voltage control potentiometer voltage that we discussed earlier. This diode really doesn't do anything except protect this transistor against a reverse bias. There are circumstances, especially when these jumpers are being removed and so on, where you could possibly end up with a higher voltage here than there is here, and therefore current would try to go backwards through the transistor and might damage it. So this diode is here just to keep that from happening. It protects this transistor, otherwise doesn't have a significant effect on the circuit. So you're developing a proportional voltage here, which is then applied to this Darlington transistor pair. This is a smaller transistor that drives the bigger power pass transistor. This is the one that's bolted to the back case of the power supply and does all the heavy work in the regulation, and certainly all the power dissipation. This resistor here is just for biasing this guy. So essentially whatever voltage is developed here is the voltage that will be presented here, which is essentially the output of the voltage regulator circuit. There is a load resistor, so there's always some load on this circuit. That's what this guy does. And then the output is presented through a series of 3 or 4 series resistors, all pretty small. This is 100 ohms. This is the current control. 1 ohm, that's the high current control. That's the one that's on the inside of the power supply bolted to the bottom of the case. And a 4 ohm resistor and a half ohm resistor, 0.0 or 0.505 ohms actually. And then from there down to the positive output of the power supply through that on/standby selector switch. So that's how the voltage regulation works. Well, I described how the control works. How does it adjust? How does it get feedback? Well, that's from this point here. This voltage here can be driven separately by breaking this point here, and likewise the positive sense is applied to the plus of the reference supply normally, but it can be disassociated and applied separately for the remote sensing. I won't get into that in any great detail, but that's why those jumpers are there. Now, this circuit here is the overcurrent protection circuit, or the current limiting. It always works to some degree, but you can arrange it to work a bit differently. So it's programmable current limiting. By turning this current control on the front panel, you can arrange for the current limiting to be something less than it would normally be. By default, it's limiting the current to 1 amp, which is the maximum design rating of the power supply. But by turning this control, you can turn it down so it limits it to something less than 1 amp. And that affects the overall resistance of this whole train of resistors here. These 3 resistors here are all part of the current limiting, and as current flows from the output of the voltage regulator out to the load, some voltage is developed or dropped across these resistors. The more current, the more drop. And then you've got this NPN transistor here with its base connected to here and its emitter connected to here. And as we know, this transistor will not conduct until you have at least the base emitter junction voltage equal to the minimum for that, for it to begin conducting. So normally, let's say that this pot is turned all the way up. The power supply is designed to limit at 1 amp. So let's say this is developing 1 amp through here, or 1 amp is flowing through here, and it starts exceeding 1 amp. At that point, the voltage drop across here finally is large enough to exceed the minimum base to emitter voltage, and this transistor starts to turn on in its linear region, and therefore it starts conducting from here to here. Well, remember this constant current source and this voltage divider function. It starts stealing current from here, and with the stealing of current from here, it changes the voltage here, because remember, this is acting like a resistor from here to ground. If there's less current available to go through here, it develops less voltage at this point. So essentially it's telling the power supply to reduce its voltage a little bit if the current here exceeds 1 amp. This is the current feedback to control the voltage. The more that it tries to exceed 1 amp, the more voltage is developed from here to here, the more this transistor turns on, the more current it steals from the constant current source, the less voltage is developed here, and the less voltage the power supply tries to develop at its output, thereby reducing the output current, or at least limiting it. Because it's a feedback circuit, it will constantly adjust the voltage to maintain that maximum current. Now if you turn this potentiometer here in the direction that would reduce current, reduce the maximum current, then it develops even more voltage for a lesser amount of current. Therefore it starts the current stealing operation at a lower current. So that's all that's about. Now for the metering circuit. Let's look at the voltage first. Here's the other two gangs of the voltage current selector switch for the meter. Remember that there's a third gang over here that operates the 2 neon bulbs, but the ones that really count are these 2 gangs here. If it's in voltage mode, then it's as shown with these shorted and these shorted, and the meter circuit here is across this point, which is the minus of the power supply, and this line here, which is the positive output of the power supply. So essentially this circuit here is across the output terminals. You've got these resistors in series and this resistor here, and that voltage is applied across that voltage divider of this resistor, and this resistor. And you can see this is 18K, this is 9K, and this is only 470 ohms. So at full scale, say you have the meter selected, or the voltage selected to the 30 volt range, therefore none of these resistors are shorted out. If you have 30 volts on the output, you've got 30 volts from here through here to this point. You're dropping most of that voltage here, and there's only a little bit of voltage dropped here, and the current flowing through there is 1.1 milliamps maximum, with 0.1 milliamp going through this shunt resistor, and the remaining 1 milliamp going through the parallel connected meter, which is a 1 milliamp meter, so 1 milliamp flowing through it will make it go to full scale. That's why the meter reads full scale when you're at your maximum output voltage. Now if we move this the voltage range switch down here to the 10 volt position, it shorts out this resistor and leaves the output voltage impressed only across this resistor and this one. But since it's a lower voltage range, it still works out that full scale will be when you develop 1 milliamp going through the meter. So that's how the meter works in in voltage mode. What if we switch the switch up here to current mode? So now the jumper is here and here, it's no longer connected to any of this stuff. Instead, this meter is in parallel with this resistor here and possibly this resistor, depending on what the current range is. If you're in 1 amp mode or 0.1 amp mode, you can see here that the function of this switch is to essentially short out this resistor when you're in the 0.1 amp mode. Essentially what you're doing is, we know you have a current going through here, and when the switch is here and here in the current mode, some of the current is going through here and a smaller amount of it is tapping off and going through the meter and then back in here. It's acting like a shunt. So the majority of the current is going through here, a little bit of it's going through here, and therefore the meter can read the appropriate current. All the resistor values are calculated to give you the proper reading. It's all coming down to the tolerance of these resistors. These two are 1% types, but this one isn't. And of course these aren't precision resistors. In the voltage mode, these are 1% resistors, but this shunt is not. It's only at best a 5% resistor. This is why the accuracy of the meter is not that great, because of these resistors here are not super high tolerance parts. They work good on paper, but in reality their values are a little bit off, and that skews the meter reading a bit. If this was a more expensive meter, you'd have more stability and more closer tolerances on those parts. One more thing I'm going to say about the remote sensing is that when these jumpers are removed here and here, this jumper and this jumper, to allow remote sensing, if you actually do have the sense terminals here and here connected out to the load through another pair of wires, then all is well and good. But if the power supply is running and you don't have those wires, you've just removed these jumpers, and the sense lines are hanging in the air, then the power supply could be influenced by stray electrostatic fields. It could have all sorts of things happening. It doesn't have any real feedback, and it's going to try to send its output voltage as high as it possibly can because it doesn't have feedback at that point. Obviously that's not a good thing, and you could possibly damage the equipment that is connected to the terminals, your load in other words, without that remote sensing being in place. So that's why these diodes are added here. The two diodes in series have the inherent forward voltage drop of the diodes 1+1, and the same thing here, and those are wired across the sense terminals. So even when these are open by failure to properly connect the sense wires, these diodes restrict the output voltage to a safe level. And it works out that I don't know exactly what it's going to set the output to, but it'll be something within a safe range for the power supply. So I think that covers everything on this circuit. I hope you found this to be interesting.